Hello everyone, and welcome back to another episode of the problem solving series. Today we are going to be covering all things work and energy. So first I'm going to go through the equations for work and the energy equations, and then explain a little bit of the concepts and how to use them, and then we'll jump into an example where you can see it in action. So let's get into the equations. Let's go through the equation for work. So work is defined as the force times the distance over which an object is traveling. Now, this is the first time that you guys are coming to two vectors being multiplied by each other, and vector multiplication is different than regular multiplication because we have to take into account these directions. So there's actually two types of vector multiplication. There's the cross product and the dot product. I'm not going to go into the cross product here because we don't need it till later. So this type of multiplication is a dot product, which is why they use that special dot to indicate and use for the multiplication. So all that the dot product means is that if we have an object moving along some distance d, and all the while it's being pushed by some force F, and there's some angle theta between them, the dot product is going to be equal to the magnitude of that force times the magnitude of that distance times the cosine of theta. Now, I am just going to say, so there's two other ways that we can think about writing this work equation and thinking about the dot product instead of this kind of pure math form. There's nothing wrong with it. It's absolutely correct. My only gripe with it is that there are many problems where they give you an angle, and just because you're not as skilled at drawing the picture and like immediately understanding what that angle means, a lot of students will just take that angle because there is one and plug it in for that theta and cosine for work, and it could have absolutely nothing to do with work. Or it could be like the complement to the angle that you actually need. So just be careful with making sure you're drawing your pictures and getting your geometry all right before jumping in and using the cosine equation if that's the one that you prefer. I am gonna be a little bit biased. These other two are the ones that I prefer, but I promise they all give you the same answer, and I'll show you how. So the other way that we can think about the dot product is that we're either taking the parallel component of F to D, so those two little lines just mean that it's parallel, so F parallel to D times D, or we're taking force times the component of D that's parallel to force. And if you are to write out in this situation what our force parallel actually is, it would be this component down here is our F parallel, and if we use SOHCAHTOA, that's the adjacent side, so it's going to be equal to the hypotenuse, or the magnitude of F, times cosine, oh, not 30, we don't have an angle, cosine theta. So it will mathematically, at the end of the day, give you the same answer, but I think I at least have found that I'm less prone to making errors if I go ahead and draw the picture and then just take the parallel component instead of doing the cosine theta equation. But like I said, totally up to you which one you want to use. Whichever one is more comfortable for you, go with that one. We then have some forces that are special in terms of energy, and these are called conservative forces. So these are the types of forces that are going to give you the same work done over a displacement, no matter what path they took to get there. And because of this, we end up writing these as potential energies within the system, or potential energy for our object, so potential to do that work instead of their own work. So the two examples we have of this in this class is going to be the elastic potential energy and the gravitational potential energy. So because of this, you wouldn't include like work due to gravity in your conservation of energy equation, which I'll talk about in a second. Instead, we think about them as potential energies, and same for springs. You wouldn't consider we consider the work done by springs as potential energy because these two forces are conservative forces. And the equations for both of these potential energies, so for the spring, it's going to be 1/2 spring constant times the change in length of the spring squared. And for gravitational potential energy, that's going to be mg times the height you are from wherever the 0 point is considered. Typically, we take that to be the surface of the Earth. But a problem could give you another reference point that's 0, so just know it's that distance from that reference point. And then the last type of energy we have to talk about is going to be kinetic energy, or the kinetic energy of motion, and that will be equal to 1/2 mv squared. So all of these come into play in kind of this ultimate holy grail, probably one of the most important concepts you need to be taking away from this physics class, conservation of energy. So what this says is that the amount of energy that you have to start with in a system, if there's no external work, is going to be equal to the total energy you have at the end of the system. So energy can change what form it's in from that initial to that final state, but the total you have isn't going to change. If you do have work going into the system, we take that into account by saying that our initial plus the work is going to go into our final. And that work is going to be the net work. So you could have multiple forces external providing work, and it would just be the total of that. So drawing pictures for energy problems is going to be very important because it's going to be able for you to organize what types of energies you have at what points, and then what you can set equivalent to one another. So we're basing everything off of this general concept that energy has to be conserved, but from your picture or from the words, you have to be able to figure out, okay, well, what types of energy do I have to start? What am I ending with? Is there work happening between? And then set up the conservation of energy specifically for what situation you have. And I'm going to go through a full example right up next where I show you exactly how this is done and how we use that conservation of energy equation.
Okay, this is a long one. We're going to hit a bunch of topics, but it'll be a comprehensive overview. So we have a 500 kilogram cart on a track launched from a spring originally compressed 0.5 meters at a height of 1,000 meters. And I'm going to go ahead and highlight some of these. What is the kinetic energy and the speed at the bottom of the track? The cart then rises to a height of 75 meters and slows to a stop in 200 meters. And what is the frictional force that would be needed to stop the cart in that distance? What is the coefficient of friction? So first step, we want to draw our picture. So I'm going to draw that we have this height, and then we're going to come up to about 75% and go on for a little while. So this distance, this vertical distance here is going to be our 1,000 meters. This distance here, right before it comes flat, is going to be our 750 meters. And then if we say it starts to go flat and we're done going any further vertically, then that means this distance is going to be our 200 meters. And we've got a spring at the top that's going to launch our cart down. So first thing I'm going to say is, so now that we've got our picture, first part of the problem, we're only looking from the top to the bottom. So I'm just going to break that up by drawing this blue dashed line. And then I'm just going to label the, I guess, 4 parts of interest, which would be here at the bottom, when we first get to the top, and then when we reach the end. So the first part, and then we want to list our energies that we have at each of these spots. So at the very top of this hill, we're going to have potential energy from the spring. We're also going to have gravitational potential energy. And then when we get to the bottom, we're going to have kinetic energy. So if we look at the conservation of energy equation, which I'll write over here. So E total initial plus W net equals E total final. So our initial position, our initial spot is going to be at spot 1. So we're going to have our potential energy from the spring plus our potential energy from gravity. We don't have any external work happening over this range. We can assume frictionless up until now. So we'll just set that equal to our kinetic energy at point 2. Then we can substitute, this is going to be 1/2 kx squared plus mgh equals 1/2. Oh, I guess first we're solving just for kinetic energy, so I'll actually just leave that as Ke. And then we can plug in our values, which I don't remember and I can't see. So I didn't give a spring constant, so I'm just going to make one up. We'll say that K is, let's make it really high. Let's make it, I don't know, 10 to the 6th Newton meters. Okay, so we'll have 1/2 10 to the 6th 0.5 squared plus 500 times 9.8 times 1,000 equals our kinetic energy. Okay, and this gives me 5.025 times 10 to the 6 joules. So that's the answer to our first question. Our second question is about the speed. So once we have the kinetic energy, we can use the fact that kinetic energy is equal to 1/2 mv squared. And then we want to get v by itself, so we can multiply both sides by 2 and divide both sides by m. We'll get 2 times the kinetic energy divided by mass equals v squared. And then we could take the square root of both sides to get v by itself. So we'll get 2 times the kinetic energy divided by mass square root equals v. And then if we substitute in our values, so 2, 5 times 10 divided by 500, I get 142 meters per second, which seems like it would be legal for a roller coaster. So this is like some old action park stuff. And if you know the reference, you're a murderino and I love you. Okay, so now let's look at the second part of this problem. So the cart has risen from the bottom another 750 meters and slows to a stop 200 meters after that. What is the frictional force and what is the coefficient of friction? So we're going to set up another conservation of energy equation. I'll box this off over here and set this up here. So I'm going to write this in a slightly different way. So I am going to write this as E total 3 plus net work. And then this is all going to be going to 0 at that part 4. So I'm just going to write that equals 0. If it doesn't go to 0, then you would write it as the total energy at part 4. And then the thing that we can notice here is that although our energy total 3 is going to be made up of some potential energy from that 750 meters and some kinetic energy left over from the very, very beginning potential energy from the spring and gravitational potential, but Since we're assuming that there's no friction on the track in between 1 and 3, we also know that the energy total at 2 is going to be equal to our energy total at 3. And our energy total at 2 is just that kinetic energy we found. So I'm going to go ahead and just use, I guess I'll rewrite that a little bit further down so that E total 3 would be the same as 5.025 times 10 to the 6th. Our W net is going to be our force times our distance. I should draw a little force diagram here just in terms of our frictional force. So with the way that I drew this, the frictional force is a kinetic, not static, but it's pointing in the negative x direction, and our displacement is going to be traveling in the positive x direction. So our W net, or our net work, is going to be minus Fk times d equals 0. And then before plugging in that d, we can go ahead and just add that force of kinetic friction to both sides. So we'll get 5.025 times 10 to the 6th equals the frictional force times d. And then we can go ahead and plug in, or I guess I'll first divide out d, and then in the next line, this is getting a little crowded, I will substitute in that 200 meters. And that is going to be equal to 25125 newtons will be our frictional force. And from that, oh my god, this became a whole mess. I'm going to erase this stuff actually. And then use this space to say for the very last question, so the force of friction is going to be equal to the coefficient of friction times the normal force. Since these, when we get to this flat section, the normal force will just be equal to mass times gravity. So we'll have Fk equals mu k times mg, and then we can divide both sides by mg. And then we can substitute in our 25,125 over 500 times 9.8, which is equal to 5.13, which is much higher than basically any coefficient of friction. So between the velocity we found, which I erased, and that this is going to be the friction you would need to stop in that time, this tells you that you should not ride this roller coaster.
Okay, and that is all that I have for energies. I guess my one last parting piece of advice, the hardest things I think about energies is personally getting the sign of the work right. So just be extra careful checking the direction that your work is taking place in. And conservation of energy is key. Happy physicsing.
Howitz, are you going to be cute? Sit. Oh my goodness! Who are you going to give them to? Who are you going to give that to? You're going to just destroy it. Hey! Get back here!